In this work, we present a state-dependent linear quadratic regulator to simplify a quadrotor's control problem. Our LQR approach unifies translational and rotational dynamics in one controller, recomputes the linearization with 10 Hz online, and applies the resulting gains in a 100 Hz feedback loop. In general, a quadrotor is an underactuated system, where we have to align the attitude with the desired acceleration. In classic quadrotor control, this is done with a cascade of controllers, but such a cascade is difficult to tune for varying tasks and imposes restrictions and multiple saturations. In a cascaded controller, position, velocity and feed-forward acceleration are used to compute the desired acceleration, which is then split into orientation and thrust. The desired orientation is controlled by the body rates, which are fed to the low-level controller together with the thrust. We show how to unify these intermediate steps and solve the problem with one LQR controller. There is one specific difficulty with this approach: the linearization. While our system states for position, velocity and orientation are in the world frame, our inputs, thrust and body rates are in the body-centric frame. This results in big input mapping errors due to deviations from the linearization point, like yawing or pitch and roll. Our solution uses the state estimate to recompute the linearization with 10 Hz. We use this linearization to solve the Riccati equation and compute LQR gains fitted to the quadrotor's actual state. These gains are then applied in a faster feedback loop at 100 Hz. In the first experiment, we show simple reference jumps. The controller follows the reference jumps with zero overshoot and a smooth behavior due to the costs on all states and inputs. In the second experiment, we fly a minimum snap trajectory using the exact same controller and costs. We follow the trajectory by setting our reference state according to the closest state on the trajectory by the Euclidean norm. We could successfully prove the functionality of our state-dependent LQR in various quadrotor maneuvers and show its performance and robustness.